In in this lecture, what we want to do is because it's very hard when you have a bigger matrices, like we said before in economics. Matrices sizes can reach easily 25 by 25, 100 by 100. We cannot use the cofactor expansion because if you use the cofactor expansion, it will take a huge amount of time to do the computation of the determinant. So what we're going to see is that some basic facts, okay, will help us in fact reduce the time for computing the determinant as well as get it in an easier way. So remember, so first, okay, so let's go step by step, okay, some basic steps. Okay, so the first one, if a matrix A has a row entirely of zeros, okay, all the entries on that row are zeros, then the cofactor expansion along that row will give us determinant of A equal 0. So if a matrix A, square matrix A, has a row of zeros, then the determinant is 0. Okay? Now, knowing that the determinant of A is the same as determinant of A transpose, this tells us what? That by the way, we can see this from the cofactor expansion, okay? Because remember, if A is equal to Aij, the A transpose is Aji. We just interchange J and I. So what we said in the cofactor expansion is that if you do it along the rows or you do it along the columns, you get the same determinant. And therefore, this is coming from that, okay? The determinant of A is determinant of A transpose, okay? It's the same. Okay, and therefore, the same conclusion we had in one for the rows is also valid for columns. If you have a column of zeros, then the determinant is equal to 0. So it's valid whether we have rows or we have what? Columns. Okay? Now we get into, because of the cofactor expansion, huh? So what happened if, so we have if A is equal to, and let us take the columns of the square matrix A. Huh? A1 is the first column, A2 the second column, etc., etc. So if A is equal to this, then what is the determinant? And what we do, we multiply one column by a constant. Huh? So we have the matrix A1, A2, we get AI, K, AI plus 1, AI plus 2, etc. So we take one column here and we multiply by one column and we multiply by, and this is the column, okay? So one column, AI plus 1, and we multiply that column by K. So if you multiply by K, then the answer is K determinant of the original matrix. Okay? So if you multiply one column or one row, by the way, because we said the determinant is the same whether you go by rows or by columns. So if you multiply one column by a number, that number comes out. So be careful, because this implies something interesting, is that if you take a matrix and you multiply the matrix by a constant, remember that in the multiplication of a matrix by a constant, we multiply all the columns, and therefore you're going to have from the first column k, from the second column another k, etc., etc. Is going to be k to the power n, the determinant of A. So if you multiply the matrix by a constant, it's k to the power n, n being the size that comes out. Okay. Next, for okay, so what happened if we exchange, so here determinant of A1, AI, AJ, AN. And what happened when we interchange AI with AJ? So if you do that, this, you will have a minus coming out. So this will give us A1, AJ, AI, AN. So if you take two columns and you interchange them, the determinant becomes opposite to each other. Huh? They become opposite to each other. And the same goes for the rows. If you exchange or interchange two rows, then you end up having that minus out. Next, what happened if we have A1, AI plus B, okay, AN. So here, what happened if we add to AI a vector B? So what happened is going to be the determinant of A1, AI, AN plus the determinant of A1, B, AN. In other words, if you have two columns, okay, two columns, and you add them, then the determinant becomes linear with respect to that column. Huh? With respect to that column, it is false. It is easy on a 2 by 2 matrix to show that the determinant of a matrix plus another matrix is not equal to the determinant of A plus determinant of C. It's very, very easy to come up with an example that shows that this is not true. But columns, if you add only two columns, okay, two columns, in other words, two columns added together, and then you can have that linearity of what? Of the determinant. What happened now if B is a constant time another column? Okay, be careful, because if the vector B here, so if this B here, okay, which is right here, if that B is equal to a constant time AI, then AI plus B, in fact, is only K plus 1 time AI, and we can take it out. Okay, we can take it out. But the point is, what happened if B, okay, so now, if B is equal a K time another column, AJ, J different from I. Okay, then when you write here, so what is now the determinant of the matrix A1, okay, and you have that K, AJ, AN. I'm talking about this one here, this determinant. this one. So that one, what's going to happen is we're going to have so we're going to have here, we can take k out, and what's going to happen is we're going to have a determinant of this matrix with two columns which are the same. Two columns which are the same. Okay? So, in this case, it's easy to see that, in fact, it's equal to 0. Okay? Two columns are the same. You're going to have AJ and AJ again, twice. Okay? So in other words, what does that mean? It means that when you take a determinant of a matrix, A1 all the way to AN, yeah? And you take a column, one column, okay? A1, let's say AI, and you add to it a constant time, another column, plus K, AJ, and I is different from J. Okay, another column. So in this case, you get the same determinant. Okay, you get the same determinant. So this reminds you of what? Of this properties, the row elementary operations. So keep in mind, all what I described here is described for column vectors, but because of the transpose, they have the same determinant. They are also valid if you take what? The rows. The conclusions are exactly the same if we take the rows. So let us just make some examples here, okay? Some examples to illustrate what we were saying. So, example. Let us take the determinant, find the determinant 0, 3, 2, 1, minus 6, 6, 5, 9, and 1. Okay? So here, we're going to use the properties we just described. 3, 2, 1, minus 6, 6, 5, 9, 1. And let us interchange the second row with the first row because we want to have the leading coefficient being non-zero. So this will give me what? Minus 3, minus 6, 9, 0, 1, 5, 2, 6, 1. Okay? So now let us take 3 out from the first row because I can factor it out. 3, 1, minus 2, 3, 0, 1, 5, 2, 6, 1. So now let us take to kill the 2, okay, that we have right here by using the 1 as the leading coefficients from the row elementary operation techniques. Then here we get minus 3, and what we are gonna do here, we are gonna take the third row, R3, minus 2, R1. So we get 1 minus 2, 3, 0, 1, 5, and then 2 minus 2, 0, 6 minus 2, that will give me times minus 2, that will be 10, because it's going to be 6 plus 4, and then the next one will be 1 minus 6 minus 5. Okay, so here I can still take, for example, let's say I take R3 minus 10 R2. So we will get what? I can do that, in other words, 1, 0, minus 2, 1, 3, 5, 0. 10 minus 10, 0. Minus 5 minus 50. 10 times 5, that's minus 55. So now if I develop along cofactor expansion, if I develop along the first column, okay, it's gonna be 1 time minus 0 time the determinant and plus 0 time. So the zeros time will disappear. So we will find minus 3 times 1 time 1, 0, 5 minus 55. Okay, and this gives me what? 2 by 2 we know, so it's going to be minus 3 times 1 time minus 55 minus 0 times 5, and that will give me plus 165. Yeah, so what's interesting here is the fact that this matrix is diagonal. This matrix is I'm sorry, not diagonal, triangular. I'm talking about when we reach here. So when we reach here, we see that this matrix is triangular. It's upper triangular because we have 0, 0, and 0. So here we have a beautiful remark using the cofactor expansion. We can show the following result, okay? So here, remark, and because the transpose of an upper triangular is lower triangular and vice versa, so let T be a triangular matrix. T equals Tij. Okay, so the components are Tij. Okay, then the determinant of T is D T11, T22, T33, etc. Tnn. What does it mean? It means this is the product of all diagonal entries. So if you go here, we could have done minus 3 times 1 times 1 times minus 55. Okay, we don't need, we could have stopped there from any cofactor expansion and so on and so forth. So this gives me this. And of course, in particular, if you have a diagonal matrix, then the determinant of a diagonal matrix is just the product of the element of the diagonal because it's also triangular. Okay, it's upper and lower triangular. Okay, next example. Let us do an example. Okay, find the following determinant. 3, 1, 2, 3, 5, 2, 4, 7, minus 2, minus 1, 1, and 5, 6, 1, 5, and 3. So what's the difference is that we have a 4 by 4 now determinant, okay? 4 by 4 determinant. So first, let us use 1 as the leading coefficient. So let me interchange the first row with the second row. Okay, so here we will get 1, 2, minus 1, 1, 3, 5, minus 2, 6, 2, 4, 1, 5, 3, 7, 5, 3, and this will be a minus, okay, because I interchanged two rows. So now let us go by removing the 3 and the 2 and the 3. So we have 1, 2, minus 1, 1, 3 minus 3, 0, 5 minus 6, minus 1, minus 2 plus 3, 1, 6 minus 3, 3. And now let us remove the 2. In other words, I'm taking the third row minus 2 times the first row. 2 minus 2, 0. 4 minus 4, 0. 1 minus 2, that's 3. And then 5 minus 2, that's 3. Okay? And then the last one will be 3 minus 3. So in other words, R4 minus 3, R1. So it's going to be, there is a minus here. 3 minus 3, 0. 7 minus 6, 1. 5 plus 3, that's 8. And 3 minus 3, that's 0. Okay. So now if we develop along the first column, so this will be plus the determinant minus 1, 0, 1, 1, 3, 8, 3, 3, 0, okay? And the other ones will be 0 times, 0 times, 0 times, okay? So here, let us remove the last one, okay? Okay. So minus 1, 1, 3, 0, 3, 3. And let us take the last row plus the first one. 1 plus 1, 0. 8 plus 1, 9. 0 plus 3, 3. Okay? And now, let us develop again along the first row now. Minus time minus 1 time 3, 3, 9, 3. Okay? Which, by the way, at this stage, this will be 9 minus 27, okay? And this will give me minus 18. So, I mean, this is what I always tell people, especially, I mean, as educators, I tell the student that, you know what? You can find easily so many combinations, a smarter way to do it. It's not like this is the optimal way to do it, okay? So it can be done using different different approach and different techniques. So the next one I want to talk about is a beautiful example, which is it has many applications. Is what's known as van der Monde determinant or matrix. Okay, so what is it? So let me start with two numbers, A, B. Okay, so that's 1A, 1B. Okay, V, A, B, and C. And that's the determinant 1A, A squared, 1B, B squared, 1C, C squared, etc. So let us start with the first ones, okay? So what is VAB? Obviously, that will be B minus A. Keep in mind the B is the second number, A is the first number. Okay, so let us look at now the 3 by 3, V, A, B, C. So remember, A, B, C means A is the first one, B is the second one, C is the third number, third entry. So we have 1A, A squared, 1B, B squared, 1C, C squared. Okay, so we're going to keep the first column, 1A, A squared, and we're going to take the second column minus the first column. 1 minus 1, 0, B minus A, B squared minus A squared, 0, C minus A, C squared minus A squared. Okay, so this gives me, so here, if I can factor out b minus a from the second column. Okay, so for example, let me do it. I'm not going to do two of them just for the sake of to emphasize something here. 1a squared. I'm taking b minus a from the second column, so this will give me 0, 1, and b squared minus a squared, that's b minus a times b plus a, and 0, c minus a, c squared minus a squared. And now let me take out c minus a from the third column, so this will give me b minus a times c minus a times 1a squared, 0, 1 b plus a, 0, 1 c plus a. And we will develop the cofactor expansion along. I mean, I can still kill the 1 by taking, let's do it. I mean, you can go faster any way you want, c minus a. Let me take now 1a squared and 0, 1 b plus a. And let's take the third column minus the second column. 0 minus 0, 1 minus 1, c plus a minus b plus a, that's c minus b. Okay, and now we have a lower triangular matrix, and we multiply the element on the diagonal. So we get the end result is b minus a, c minus a, and c minus b. Okay, that's v of a, b, and c. Okay, so just to give you an idea here, we can do v, a, b, c, d, same technique. It's a little bit complicated because you are going to have a cubed minus b cubed, or b cubed minus a cubed, which is b minus a times b squared plus ab plus a squared. So knowing this formula from algebra, you can prove that this is b minus a times c minus a times d minus a, then c minus b times d minus b times d minus c. So look at how the numbers are coming from to the right minus to the left. Okay, the numbers. Okay, so if I take now in general, okay, v of x1, x2, etc., xn. So what's going to happen is we're going to go x2 minus x1, okay, x3 minus x1, etc., till I reach xn minus x1, okay, plus I'm in time, and we go now x3 minus x2, etc., till xn minus x2, etc., and the last one will be xn minus xn minus 1. So in fact, we have a formula, an abstract formula here, x1, x2, xn equal the product of xi minus xj, but this time I is greater than j, greater than j. So it's a beautiful formula. It's a beautiful formula. Which, by the way, this van der Monde determinant has many applications. In abstract linear algebra, of course.